If you're a physics student, then you should know how to derive the Euler-Lagrange equation. To begin with, we define something known as the Lagrangian function, which can in general be thought of as the kinetic energy minus the potential energy of the particle of interest. For example, a free particle, i.e. one that's not moving within some potential, has a Lagrangian given by this expression here. Using this Lagrangian, we define a functional, so something that takes a function and gives you a real number, known as the action, which is the integral of the Lagrangian over some time period. Now, Hamilton's principle of stationary action in classical mechanics states that the trajectory that a particle takes is the one that makes the action stationary. Mathematically, we can formulate this statement using something known as the Gateau derivative, and use the vanishing of this derivative to help us find the classical trajectory. Rather like how in normal one-dimensional calculus, you can use the vanishing of the first derivative to find stationary points. Now, the notion of this Gateau derivative might seem a little bit strange, but all we're really doing is slightly perturbing the general path on which the action depends, x of t, using some test function epsilon of t that's controlled by some parameter s, and then calculating the change in action to first order in this parameter s. Our perturbation in x of t of course induces a perturbation in x dot of t, and thus applying the chain rule we get the following expression for our Gateau derivative. We can work with this expression a little more by reversing the product rule to rewrite this final term as follows. The reason for doing this is twofold. Firstly, we get a total derivative that we can easily integrate, and we get a term that depends on the variation of x of t evaluated at the initial and final times, so the boundary points of this trajectory. Because we want the system to evolve from a fixed start point to a fixed end point, we stipulate that the variation evaluated at the initial and final times must be 0, and therefore this term drops out. And the second reason for this step was that now all of the terms are proportional to the same arbitrary test function variation, which we can factor out and then employ the fundamental lemma of variational calculus, which allows us to say that if we want this entire first order functional variation or Gateau derivative of this functional to vanish, then what this means is that for well-behaved enough test functions, epsilon of t, what's inside the brackets must vanish. And doing exactly this, you'll see that we recover the famous Euler-Lagrange equation, which eventually, by calculating these partial derivatives, will turn into some differential equation that we can solve and apply some initial conditions or boundary conditions that will give us the classical trajectory as our solution.